Hello friends, welcome back to this online certification course on watershed hydrology. I am Rajendra Singh, professor in the Department of Agricultural and Food Engineering at Indian Institute of Technology, Kharagpur. We are in module 3 and this is lecture number 5 and the topic is flow duration curve and flow mass curve. In this lecture, we will introduce flow duration curve, then flow mass curve. Then we will see how to compute storage amount using a flow mass curve and how to compute the maintainable demand as well as the variable demand. Now, starting with the flow duration curve, or which is popularly called as FDC, it is a cumulative probability curve that shows the percentage of time during which a particular discharge value is equaled or exceeded. So, this is the curve which you can see on the right. The y axis of the curve represents the flow values and the x axis represents the percentage of time the corresponding flow values are equal or exceeded following the Weber formula P equals to m by n plus 1. So, as you can see here, this is the discharge plotted against probability of accident in percent. And if you remember, we discussed in the rainfall frequency that Weber formula is one of the very popular formula for frequency, like carrying out frequency analysis. What is done here is that when the discharge series we get, we arrange that in the descending order of magnitude and assign rank numbers. M is a rank number. So, rank number 1 is given to the highest value, m equal to 1, and m equal to 2 to second highest value, and m equal to n for the last value in the series. So, n is the number of data points in a series. So, that is how we will formula, we calculate the probability of accidents and then we plot this curve. FDCs are useful for design of structures on a stream. So, obviously, it is used using a stream data, this curve is plotted. For example, a structure can be designed to perform well within some range of flows, such as flow that occur between 20 and 80% of time or some other selected interval. So, here if you see the probability of accidents, so obviously at the rightmost corner when the probability of accidents is 90 or 100, then this is the low flow area, wherein on the other extreme when the probability is low 1%, 2%, then this is the high flow area, and in between this is the medium flow. So, we have 3 distinct flow regimes here: high flow, medium flow and low flow. So, obviously, if we know that a particular structure can perform within certain range, then we can find out what is the probability of accidents of that range, and this is of course used for drinking water supply and for designing the hydropower plants, because hydropower plants basically they work mostly in the medium range of flow. So, that is how we decide what should be the capacity and all based on this flow duration curve. They are an essential tool for flood risk assessment by providing information on high flow events and their return period. So, obviously, we know that if it is say 2%, if we talk about say 2%, then we know that t equals to 1 by p. So, the t will be 50 years. So, from here we can find out what is the 2%, what is the magnitude of flow, and of course, flood, when we talk about flood, we are in the interested in the high flow. So, knowing that also we can find out what is the possibility of getting a particular magnitude, and then what will be the risk, and then what will be its return period, and then accordingly preparedness could be taken care of. Then to evaluate, they are also used to evaluate ecological health of rivers and streams by examining the variety of flow conditions that support aquatic habitat. So, that is talking more about the low flow conditions. For example, a particular fish species may not survive if the flow is too low. So, obviously, we have to find out what is the low flow magnitude, so that we can provide a or rather we can put only a typical type of fish, or if a particular fish survives in a particular stream, then we should ensure that a certain minimum flow is always available there. So, that is how this flow duration curve also helps us in deciding the environmental flow that is required at a particular place. And understanding the flow regime helps in the studying sediment transport dynamics and erosion and deposition process in the river stream system. So, of course, because sediment transport of course is directly connected to flow also, because we saw that aggradation or degradation can mar the stream flow. So, obviously, for sediment transport dynamics also the flow duration curve can be used. Let us take an example here. The monthly discharge of a small stream is given in the following table. Derive the flow duration curve and calculate the 60% and 75% dependable flow for this river. And here you see for different months of year, starting from January to December, the flow magnitudes are given, that is starting 0.36 in January to 0.4 in December. Of course, the max will be somewhere here in July, August. So, it is here you can see in the July the highest flow is there. So, obviously, as we have already discussed that in order to draw the flow duration curve, we first need the probability of exceedance for different flow magnitudes. So, we arrange the data in descending order of magnitude, as you can see here. It is highest value at top and bottom most value is the lowest, and then we assign rank 1 to the highest value. So, 2.59 which was highest in July, that is assigned rank 1, and 0.36 which was lowest is assigned a value of rank 12, because 12 monthly data. So, 12 data points are there. Then Weyer's formula is applied to determine the probability of occurrence, and so we know Weyer's formula m by n plus 1, n is 12, m already we have calculated. So, the probability of occurrence for different flow magnitudes we know, and of course, then using these two values the discharge is plotted against the probability of occurrence to get the FDC. So, we have discharge values and we have the probability of occurrence. So, we will make this curve. So, either this discharge this or this column we can use and then plot the curve, and then obviously, then we can find FDCs can be used to obtain the flow at desired probability, and in this case we require the flows is 60% and 80%. So, 60% and 80% the flow values can be read here, and the flows in this particular data series are 0.48 at 0.3, 0.48 at 60% of probability and 0.3 cubic meter per second at 75% of probability. So, this is how FDC can be used for finding out flow at different probabilities. Now, let us come to flow mass curve, which is a plot of cumulative runoff amount of flow volume against time. So, basically it is a graphical representation of equation 1. This is the equation which is nothing but integral equation of the QT over time, and where VQ varies with time. So, obviously, QT we know that Q is nothing but the stream flow, and we saw different ways of determining or measuring stream flow. So, if we know stream flow values and then we integrate that, we will get the cumulative runoff amount or cumulative flow volume. And the lower limit of this integral denotes the start of the time or of the curve. So, this value can be this is 0 to t, that means we are starting at time 0 and up to time t we are talking, and this value could be taken other than 0 also. So, that we can means if suppose we are talking about monthly data. So, we might be interested in say April to October what happens. So, we can start over 4 to 10 and then integrate the value to get the values, and this is how. So, cumulative flow volume in cubic day, we are using a typical of course, the volume means we can put in cubic meters, but just to keep it simple we use it cubic day, so that the numbers are reasonable, and of course, here the time it could be month, it could be weekly, whatever could be there, and this is the black line is nothing but the mass curve. At the time the curve gives the cumulative volume of flow up to that time. So, suppose I want to find out what is the cumulative flow up to say month 4, then obviously I can find out reading this curve. and the slope of the curve at any point is the rate of flow at that time. So, I can find out the slope of the curve at any given point, and that will tell me the rate of flow at that particular point. The slope of the line connecting any two points is the average flow rate between those points, say for example, line AB. So, if we draw line A, these 2 points, the first point and the last point, and we draw a straight line joining this edge, the green line here, then it is nothing but the average flow rate. So, that is the average flow rate we can expect over the entire period for which the flow mass curve has been drawn. And Ripple 1883 was first to use the term flow mass curve. That is why this diagram is also called as Ripple diagram. So, it is flow mass curve, flow curve, or Ripple diagram. Now, coming to application of flow mass curve, they have several practical applications, that is, they are useful in determining the storage capacity of a reservoir. So, basically the practical, if we look at the average flow rate, if enough storage were provided, then the reservoir would be able to supply at this average rate for the period of the curve. So, that simply means that we have drawn this flow duration curve, and then we have found this average flow rate. That simply gives an idea that during this period, this particular storage structure, which is reservoir, would be able to supply us at this average rate of, that is the slope of the line will tell us the rate, and that is the average rate. And the straight line average flow rate can also be called the supply line. So, this is the average flow rate or average supply line, and that much we can supply over the period of the curve from this particular reservoir. So, basically we can decide on the storage capacity of the curve, like if we are interested in supplying at a particular rate over a given period of time, then obviously we can find out using the flow duration curve what should be the storage capacity in order to be able to supply that, and we will see that in next slides. Before that, this just let us say that generally reservoirs, they use what is called as CSZ, or concept of storage zoning. So, basically the storage zone is divided in different zones typically in reservoirs. So, at the bottommost you will find there is a dead storage, that is a minimum pool level, and this is this dead storage is not really useful water, it is not the useful storage, but basically it is provided in order to tackle the sedimentation over a period of the life of the structure. So, over the period of life we expect that sediment will come, and they will be deposited at the bottom of this reservoir. So, in order to take care of that, dead storage is provided. Then the day to day operation of the reservoirs, for that we provide active storage or minimum useful storage. That is, we define a normal pool level, of course, we have minimum pool level. So, whatever stored water is there, that is called active storage, and that is used in day to day operation of reservoirs. So, that is active storage. Above dead storage, active storage, we have flood control storage, like because reservoirs could be used as flood control structures. So, we do provide flood control structures, and of course, there is a surcharge storage also, like if more than expected flood comes, then obviously we will release that, and of course, we have spillways provided in order to spill over the excess flow or the flood, and then we have sluiceways at different elevation, they can be provided depending upon the purpose for supplying the amount of water daily basis in order to meet the various kinds of demands. And this is a typical dam or reservoir. This is Kangsavati dam and reservoir, as you can see the dam and the reservoir water you can see. It is located in Mukut Manipur, Bankura district of West Bengal. So, coming back to the use of flow duration curve in deciding the storage capacity of a reservoir. So, obviously, for that we need to carry out storage amount computation. So, let us say consider a reservoir that is full initially or at the start of the dry season. The typically reservoirs are designed and operated in such a way that when the dry season comes, at the beginning of the dry season, they should be completely full. So, we have enough water to meet the demands during the dry season. So, at any point, any time, the amount of water withdrawn from the reservoir is the difference between the cumulative supply and cumulative demand from the beginning up to that time. And maximum of this amount wherever it occurs is storage S to be provided, that is the storage S capacity we are interested in. Now, here we see that red line is the supply line, that is this red line represents some Vs or the storage the flow volume, and then obviously we will also have to have a demand volume. So, how much demand is there from which has to be met from this reservoir. Now, let us say that hypothetically that this is one of the demand lines, the bottom one, this one. Now, compared to this supply line, and if you look at this demand line, then it is a ideal situation, because supply is throughout greater than the demand. So, supply is throughout the greater than demand, and that means we do not really require any storage. You don't have to build a reservoir basically, because you have all the time supply greater than storage. But suppose a picture where our demand line is like this dashed line here, where storage is required at certain period of time, could be positive, because at times the demand is more than the supply. So, here you can see here this period, in this period the supply is more than demand. So, no problem. But if you look at this period here the demand is more than the supply. So, obviously, you have to have water available in your reserve to be able to meet that particular demand, and that is where that is how we decide the storage. And so, the maximum so wherever we have to keep in mind the lean periods, that is you see that this is the peak flow which is coming, and this is the lean period. So, we have humps and valleys. So, humps basically represent peak period, wherein there is a valley here or valley here, they represent the lean period. That is, lean period means when your supply is low than the demand. So, obviously, for all the lean periods we have to find out what is the storage required in order to meet a particular demand, and then wherever this storage requirement is high, that tells us that this is a storage we must be available with us in order to be able to meet that or sustain that demand. So, we can express as that is storage is maximum of some Vd minus some Vs, that is demand line minus supply line. So, wherever the demand is more than supply, that will tell us what is the total supply required, and Vd and Vs, as we have already seen, is cumulative supply and cumulative demand. So, when the mass curve of supply and demand are plotted, the maximum difference in their ordinates give the maximum cumulative difference with the storage amount S of that dry period, and the value of S are calculated for different dry periods, and largest of this value is the minimum of storage required for the particular reservoir. So, suppose we want to estimate the storage requirement, then of course, we draw demand line of known demand rate. Say for example, our demand rate is 50 cubic meter per second, tangential to various humps in the mass curve. So, this is a mass curve we have plotted, and we identify the humps, different humps, and then from there we draw a line having a slope of 50 cubic meter per second, and of course, we know how to find out the slopes at. So, I mean the slope of this line will be vertical minus this vertical divided by this horizontal. So, any place we can find out what is the slope, and that slope has to be maintained at 50 cubic meter per second. Then find the vertical distance between these demand lines and their respective valley bottoms. These represent the required storage to meet demand. So, for example, here from valley bottom to this particular line is S1. from then again in the second valley we have S2, third valley we have S3, and we said that I mean this is a storage required to meet this particular demand in this particular period. This is S2 is required to meet the demand in this period. So, basically the storage required as far as the reservoir is concerned, the maximum of SI wherever it occurs, that gives us what is the storage required in order to sustain this particular demand. Let us take an example, a simple example here, and let's compute the minimum reservoir storage required to maintain a demand of 50 cubic meter per second. Monthly reservoir flows to the reservoir available as follows. So, these are the different months January to December flows are given, and to simplify the plotting of the mass curve, assume each month has 30 days and solve the problem both graphically and arithmetically. So, both the problem can be solved both graphically and arithmetically, as we will see. So, this is the supply and this is the demand we have to maintain. For that we have to find out the storage. So, obviously, as we have seen that first thing we have to do is that we have to put the monthly flow volumes and cumulative flow volumes we have to compute. So, we have number of days in different months, and we have mean flow values given. So, monthly flow volume we can find out, that is column 2 and column 3 will give us monthly flow volume, and cumulative of this particular column 4 will give us the cumulative flow volume. So, this is what we have obtained. So, using this cumulative flow volume we can draw the flow mass curve. So, cumulative flow volume plotted against time to obtain the flow mass curve, and for simplicity of plotting we have taken all months are same, I mean equidistant, that is what we have done assumed. And then what we do is a demand line having a slope of 50 cubic meter per second drawn tangential to the hump at the beginning of flow mass curve. So, in this particular example you see we only have one lean period, and that is one hump at A. So, starting from A we draw a line AB such that the slope of the line is 50 cubic meters per second, that is the demand which we have to sustain. And to compute the required storage, a line parallel to demand line is drawn tangentially to valley bottom to mass curve, say line A1 B1, and this is just for accurately determine the value of S. So, what is done is that we identify the valley bottom and we draw a line having slope parallel to this line AB, that means having the slope of the same 50 cubics. So, this A1 B1 is parallel to AB, and the vertical distance between these two parallel lines gives the minimum storage S required to meet the constant demand rate of 50 cubic. So, this vertical distance vertical gap if we calculate or we find out, then that is nothing but the storage required, and from graph we find the storage S that can be that is required to sustain a demand of 50 cubic meters per second is 2300 cubic days. So, this much volume of water must be stored in the reservoir if we want to sustain this supply the average supply of 50 cubic meter per second. So, this is graphical solution. So, arithmetically also similar procedure, the flow rate is given. So, flow volume we will calculate for different months, and the demand rate is constant 50. So, we will also calculate the demand volumes. So, flow volumes and demand volumes we have calculated, and then we will calculate the deficiency in cubic days, which is column 2 minus column 5. So, column 2 is column 2 minus column 5, no, that is this is a multiplication, sorry, column 2 minus 5, deficiency is column 4 minus column 6, this needs correction. This is column 4 minus column 6, that is cumulative flow volume minus cumulative the demand volume, that will give us deficiency for different months. And then what we do, we cumulative of successive negative values, that is where the deficiency is there, these are the here these are the 4 months where negative values are there or deficiency is there. So, we get the cumulative excess demand during this period, and of course, then we have cumulative excess flow also for other than this period. So, from here we get that it is the total deficiency which is there during the year is 2009 and cubic days, and that is the minimum storage volume that is required. So, the maximum cumulative excess demand is the month of June, and it equals 2009 cubic days, and this is the value of storage required to meet the demand of 50 cubic meter per day. This value of storage differs from one obtained graphically. In the graphical solution, we got 2300, where we got 2900 arithmetically, and that is simply because in arithmetic calculation flow is assumed to vary linearly from one month to other, while in the graphical solution the mass curve is curvilinear. So, we have plotted and that was curvilinear, and that is why this difference, the minor difference on solution comes. And it may be noted that the last column in the table indicates if the reservoir is going to be refilled, and if you look at the table here, that we had 2009. So, right here in the month of August, this reservoir will be refilled. So, this is how we can find out the storage requirement. Now, the inverse of the problem is that we already have a storage available in a reservoir, and we want to compute what demand this reservoir can sustain, and the maximum firm demand that can be maintained by a reservoir is called the firm yield. So, that is what we have to find out. So, earlier the demand was known and the required storage was determined. Now, storage is known and we want to find out the demand. So, that is the problem is just reverse. So, from the valley bottom of the mass curve, for known storage we draw a vertical line, and then of course, we corresponding to that storage value, we find the different demand slopes. So, different demand slopes will be there, and of course, the minimum of these values is the maximum firm demand maintained by the reservoir, which is denoted by D. So, earlier case we were maximum of S, now it is the minimum of D, that will tell us that this is the demand, this is the firm yield or the maintainable demand which the storage in the reservoir can sustain. So, we will take an example, compute the maximum uniform demand rate that can be maintained by the reservoir with storage of 3000 cubic day, and monthly reservoir flows to river flows to the reservoir as given. So, here we have the reservoir inflows are given, and we know that this is the storage capacity, and here also we will assume 30 days for a smooth plotting of the curve. So, monthly flow volume and cumulative flow volumes are calculated as we did earlier, and then of course, we will plot the mass curve. And as we said earlier that a vertical line of 3000 cubic meter per day, which is the storage available, is drawn at the valley bottom of the mass curve. In this case also we have only a single valley. So, we will find out the valley bottom and draw a vertical line representing this represents 3000 cubic meters day times day storage available. Parallel to this line, a tangent is drawn. So the line is drawn at tangential to the hump of the mass curve and passes through point C. So here we starting from here, we draw a line tangential to this point M, and that crosses through point B. And then we parallel to this line, we similar way we draw this line M1 N1, and anywhere if you measure this should be this gap should be 3000 cubic day. If it is so, then our slope is fine, and then we will find out the slope of the line, and in this case we find that the slope of line Mn comes out to be 63 cubic meter per day. So, that is the demand which can be sustained by this reservoir when the storage available is 3000 cubic days. In the case of mass curve having more than one valley, the exercise repeated for each valley, and lowest of demands is the maintainable demand, like we saw that D1, D2 we calculate, and minimum of that will tell us the maintainable demand. Similar fashion, we can also consider the variable demand, that is because in the reservoir basically their demands could be of various nature and they keep on changing. For example, if you consider irrigation, so that irrigation supply changes throughout the year. Similar that could be also true with the domestic water supply. Of course, that does not fluctuate too much during the year, but irrigation is one that fluctuates. So, this could be say variable demand mass curve. We remember we up till now we were assuming a constant slope line, that is constant demand, but in this case we can also have a variable demand, and this demands needs to be taken into account for designing the storage reservoir. So, obviously, variable supply and demand mass curve will be used for determining the reservoir storage. So, we will take an example, compute the amount of storage needed to meet the demands varying from month to month. The reservoir area is 10 square kilometers. For converting rainfall to flow to reservoir, a runoff coefficient of 0.6 can be assumed. Prior commitment are 100 millimeter per unit area for each month. Mean flow, demand, rainfall and loss data per unit reservoir are given. So, all the data is available. So, mean flow is there, societal demand is there, monthly evaporation losses are there, other monthly losses are there, and monthly rainfall value is also given here. So, obviously, we have this is the inflow, this is the rainfall, and these are demand, societal demand, prior commitment, evaporation losses and other losses. So, that means this the total demand we know for each month, and that comes out to be 360 for example for January, that is sum of all these demands. And we also know total inflow, that is the total inflow is of course the inflow which is coming, and of course the runoff which is 60% of the rainfall, because our runoff coefficient is 0.6. So, that is why 760 is the inflow during the month of. So, that means for each month we know the supply and demand, and like previously we will find out the deficiency, and continuous deficiency wherever we get, the sum of that will tell us that this is a storage required. So, in this case we can see that the required storage per unit reservoir area is 1042 millimeters, because we are doing all in depth months, and again very next month this reservoir will be filled also. So, because the reservoir required storage is 1042 millimeters, reservoir is 10 square kilometers. So, multiplication of that will give us the storage required for the reservoir, which comes out with 10.42 million cubic meter. So, reservoir should have a storage capacity of 10.42 million cubic meter to meet the variable demand. So, as you see that we saw the FDC, flow duration curve, which is a flow mass curve, and we also saw how to use the flow mass curve in order to design reservoirs, or if existing reservoir is there, and then how to find out what demand this reservoir could support. So, please feel free to give your feedback on this discussion, and also raise your questions or doubt, so that can be replied on the forum. Thank you very much.